So our final presentation for advanced cryptography is Shor algorithms to break Rsa. This is done by Sanjay, Iltarish, Syed, and Mizanur.
So we're gonna start out with like a bunch of background information. So until the 1970s, cryptography was only based on symmetric keys. This means that the sender encrypts the information that is to be sent using a unique key. Once the encrypted information arrives at the destination, the recipient uses an identical key to translate the information. For instance, if a sender called Alice wants to send a confidential message to a recipient known as Bob, she will convert the message using a unique key. In this way, the normal text is converted to ciphertext that is hard to understand. Once Bob receives a ciphertext, he uses a special key that is identical to the key used by Alice to translate the information back to normal text. Therefore, Alice and Bob communicate privately. For them to communicate privately, they must first share identical keys. However, the primary challenge in this case is establishing a communication key without being physically present. Another disadvantage of this model is that if Alice wants to communicate with multiple people, she will have to assign each of the persons a different key. She will also need to keep a track of all the special keys assigned. In order to manage these keys, Alice will be required to send thousands of messages to generate special keys. This is where the RSA comes in handy. The RSA algorithm was formulated to solve these challenges. The RSA algorithm is considered to be a public key encryption method. To understand this model, it is important to note that lock and unlock are inverse operations. This means that Alice, the sender, can buy a lock and send it to the recipient. The recipient will then insert his message, lock it, and send it back to Alice. Since Alice has the key, she will easily open the message without having to share the keys. In this scenario, Alice can publish the lock widely and let multiple people use it to send messages. Also, she will not be required to maintain multiple keys. The keys are split into two forms, decryption and encryption. They form similar operations but inversely. In order to generate these keys, prime factorization is considered. The complexity of prime factorization makes it ideal to be applied in cryptography. Each number has a prime factor that can be considered as a secret key. Let Alice and Bob be communicating parties who communicate over a public tunnel, which can be intercepted by Eve. If Bob wants to send a message to Alice, then Alice would choose two large primes, P and Q, and a positive integer x, such that the GCD of x and P minus 1 and Q minus 1 is equal to 1. And then Alice sends n to Bob through the channel, which is n, P, Q, and x. And then Bob sends h, which is equal to m to the power of x mod n. In this scheme, we assume that GCD of m and n is equal to 1, and the message is less than the number. So in this case, the lower m is message, and then n is capital N is the number that is being sent. So here you see on the slide what I just went over. So n is equal to p. So n is equal to pqx, and then h is equal to m to the power of x mod n, and then we assume that the GCD of those two numbers is 1, and m is less than n. So, in 1994, Peter Shor proved that it's possible for a quantum computer to factor a number n in polynomial time, thereby breaking RSA. Taking advantage of the speed of a quantum computer to check all the possible divisors in parallel, the classic algorithm is not going to work. The important thing to consider for a fast and accurate factoring algorithm is to take advantage of the factoring problem itself by using mathematical properties of factoring. For instance, we can assume that we have a positive integer. Although we don't know its prime factors, we can say it will have exactly one factorization. Even though this won't help in solving factorization, it will help us with the hope that it has another mathematical property we can use. In this case, we'll be using the ability to reduce the prime factorization problem into a problem of order finding, also known as period finding. So in this example here, we're given a sequence 2, 4, 8, 16, 128, 256, 512, 1024. So now let's create a sequence by modding the above sequence by 15. So the new sequence is 2, 4, 8, 1, 2, 4, 8, 1, 2, 4. From analyzing the above periodic sequences, we can say that it has a period or order of 4. Now, if we create a new sequence by modding the powers of 2 with 21, we will get a sequence 2, 4, 8, 16, 11, 1, 2, 4, 8, 16, which is right here. The above periodic sequence will give a period of 6. Euler in the 1760s discovered a pattern to the period finding problem, assuming n as a product of two prime numbers p and q. This sequence will be x mod n, x squared mod n, and x cubed mod n, and also x to the power of 4 mod n. If x can't be divided by p or q, then the sequence will be repeating with some period that evenly divides p minus 1 and q minus 1. In the example above, we have n equals 1, n equals 15, and n equals 21, and x equals 2. The prime factors of 15 is p is equal to 3 and q is equal to 5. So p minus 1 and q minus 1 is equal to 8, which can be divisible by the period of 4. The prime factors of 21 is p is equal to 3 and q is equal to 7. Then p minus 1 and q minus 1 is equal to 12, which is divisible by the period of 6. By finding the period of the sequence, x mod n, x squared mod n, x cubed mod n, and x to the power of 4 mod n, we will be able to understand something about its prime factors of n, divisor p minus 1, q minus 1. If we find out several random divisor p minus 1, q minus 1 by brute forcing different random values of x, then we will be able to find out p minus 1, q minus 1 by multiplying the divisors together. If we successfully determine p minus 1, q minus 1, we determine p and q from it. However, there still exists a problem with applying observation to factorization problem. Although the sequence will start repeating x mod n, x squared mod n, etc., at some point, the steps before it starts repeating and can be large as n. In RSA, it's a very large number. However, with the help of quantum algorithm, we can determine it in a good amount of time. So now we go on to the Shor algorithm, which will be explained briefly in the introduction, and then we'll cover more of it as we go on. So Shor algorithm has two parts: turning the factoring problem into a period finding problem, which can be computed via a classical computer. The second part is to find the period using quantum Fourier transform. Quantum Fourier transform is responsible for speeding up the algorithm. We will talk about these two concepts later in the presentation. So the purpose of Shor is to factor a large integer n we assume is odd. So the Shor algorithm utilizes the properties of superposition using number theory to determine the period of a function. In encrypting data, we have seen that two large prime numbers are factors and used as private keys. This can be determined using 4 steps as described below. So you consider a number n, and let's say that number let's say that number is a. A has to be less than n, and it should not be a factor of n. And then step 2 would be determining r, and then this is the period of a mod n. And then step 3 is establishing r that is even, and a to the power of r divided by 2 plus 1 is equal to 0 mod n. And then step 4 would be the is not equal to 0 mod n, sorry. And then step 4 is considering the GCD of a to the power of r divided by 2 minus 1 and n. Q is equal to the GCD of r divided by a to the power of r divided by 2 plus 1 and n. In this case, you can find p and q, which are prime factors of n. However, in the second step, one has to find the period of a mod n. From the steps above, r can be determined using a to the power of r is congruent to 1 mod n. Again, we will go over these steps later in the presentation. So finding the period of small numbers can be pretty easy. However, things get complicated when values of n increases. This is where the Shor algorithm can be utilized by using quantum Fourier transform. The figure here basically shows the difference between Shor algorithm and like the best classical algorithm to find the prime factors. So now that the introduction is done, we're gonna go to the objective of this project. So we know the basics of RSA and Shor's algorithm. from the introduction. Hence, the objective of this project is to show in depth how Shor's algorithm can be used to break an RSA crypto system by finding two primes P and Q of some number n. So now we're going to talk about the classical component in detail. So as we went over the steps before in the introduction, we pick a number x less than n at random. In the introduction it was a, but in this case let's say the number is x. So we need to make sure that x is not a factor of n. And then in step 2 we find r, which is the period of number x mod n. And then step 3 is we check that r is even and x to the power of r divided by 2 plus 1 is not equal to 0 mod n. And then step 4 is finding P and Q. So there's a little typo here, but this should be Q. So just so you know, this is P and this is Q. And we let P equal to the GCD of x to the power of r divided by 2 minus 1. And n, the GCD of that. And then Q would be the GCD of x to the power of r divided by 2 plus 1 and n. Again, we saw this in the introduction, so now we have to focus on step 2 because that's the hardest part. We're trying to find r, which is the period x mod n, and x to the power of r is congruent to 1 mod n. R can be easily found in if the numbers n and x are small, simply by brute force. So if you take a look at this example, we have n is equal to 7, x is equal to 2. By brute force, we can find r in this case. So we let r equal 1, and then we mod that by 7, we get 2. So the next r would be 2. So 2 to the power of 2 mod 7 is 4. Then we try 3. 2 to the power of 3 mod 7 is 1. And now we have our period because it took 3 trials for us to get 1. So therefore the period's 3. But it's not so easy when you have a big N. And that's how it is in the real world. So to find r, the period, for a big N, we need the quantum component of Shor's.
So now it's time to put everything together to solve the prime factorization, the key component in hacking the RSA algorithm. Before we dive into period finding, we need to know the phase estimation. It's a very abstract concept, but yet it's a very important tool in quantum computing. So the phase estimation algorithm can be summarized into this following quantum circuit with a chain of unitary operator U. And to crack the RSA, we need to find the period of the modular x raised to the power of a mod n. And so we reformulate our period finding problem into a phase estimation problem to find the period of x over x raised to the power of a mod n, and find the eigenvalue of u. Since you have r numbers of eigenvectors, the phase phi in the phase estimation equals to s over r, where s is an integer in the range of 0 to r minus 1, and each eigenvector corresponds to a different value of s, demonstrated by the formula right here. We just compute the superposition of all the inputs. If we pass it into the phase estimation, we will compute the phases of all the eigenvectors in parallel. For example, when we make measurements, each peak here in this graph represents the phase value of one of the eigenvectors. So to put it all together, we have 2 registers. The second register should have enough bits to hold n, and then the first register have t qubits, which we have enough precision to estimate the phase. We can pick t as t equal to the 2m qubits, where m is equal to log n upper bound. We use t Hadamard gate to prepare the first register into uniform superposition and prepare the second register to be 1. And then we applied a series of controlled U gates. This will bring the system to the following equations, and then we can estimate these equations by solving the previous equations. And then we applied the inverse QFT to the first register. The superpositions become number 4, this equation is right here. And then we can effectively measure the first register. And last, we can apply the continued fractions algorithms. We have a complete period finding algorithms for the Shor algorithms. And then we can, So for now, let's get into the time complexity of the Shor algorithms. On a quantum computer, the factor of an integer n, Shor's algorithms run in polynomial time. Having said that, a comparison of numbers of steps on a quantum computer versus number of steps on a classical computer is problematic for a variety of reasons. So first, the number of steps depends on the exact architecture of the quantum computer, which we won't know until one is built. And the second, the time required for a single step on a quantum computer is likely to be quite a bit slower than the single step on the classical computer, which again, we won't know how much slower until one quantum computer exists.
All right, now let's just take a look at the implementation of Shor algorithm in Python. Although it's impossible to simulate a quantum mechanical system on a classical computing device without incurring exponential slowdown, the simulation is only tolerable to observe for relatively small numbers. The simulation implements all of the implementation that we implemented implements all of the steps that Syed has discussed in the previous slides. For factoring an n-bit number using 2n plus 3 qubits. In this implementation, the modular exponentiation is carried out using modular multiplication and shifts. Furthermore, it uses the semi-classical quantum Fourier transform, pulling the final measurements of the X register through the final inverse quantum Fourier transform, allowed to run the 2n modular multiplication serially, which keeps one from having to store the 2n qubits of X. So let's just take a look at the implementation or like the code. So right now we are trying to like factorize 77. This might take a little bit. So it took about so here it found the factors of 77, that's 7 and 11, and the execution time, this is the execution time, and we are trying, we can just skip this part, and we use 91. I'm going to just skip to the end of the program. So like this execution time, and these are the qubits used, and we used it for 15. Again, that's execution time. It's quite fast for like smaller numbers. So this is 35. That's execution time. Again, it's really fast for like smaller numbers. We have also tried to factorize large numbers like 667, which took about 19 minutes to factorize. So as the number goes up, the execution times goes up. That's implementation. So this is the most important part of the code, which executes the 2n modular multiplication conditioned on a control qubit. That's the control qubit in a uniform superposition of 0 and 1. The control qubit is then measured after performing the semi-classical inverse quantum Fourier transform, and the measurement outcome is saved in the list measurements, followed by a reset the control qubit to state 0. So this is a runtime analysis of factoring a set of numbers from 15 to 105. These are the numbers we use for factorization, and this is the execution time, and these are the number of qubits the program used. We have the factors, the n on the x-axis, and like the time that it took to factorize on the y-axis, and that's it for like the implementation.
So through the principle of superposition in quantum systems, we can create useful memory components that are on the scale of an atom or smaller. These quantum memory registers may facilitate exponential computational speed increases by taking advantage of quantum parallelism. Peter Shor has developed an algorithm which makes factoring large numbers traceable, and and doing so has drawn great attention to the field of quantum computing. Due to Shor's algorithm, we may someday have to turn to other means of encrypting data than currently employed because it can break RSA.
And these are the work that or the reference that we use for the project. This is where we got the code, Python implementation, and
these two sources were used for the introduction part, and these two sources, and along with this Wikipedia link, was used for the phases and explaining the classical component.
Thank you.